Welcome to Lecture 1.3, Hello World for Introduction to Programming in Mechanical Engineering. By the end of this lecture video, you will have an understanding of what it means to write a hello world, how to use the command window for basic code execution, how to write a simple script in the editor, how to format variables in output messages, and all of the various formatting codes in MATLAB. This slide, the table of contents, contains hyperlinks to each of the sections to make the downloaded PDF easy to navigate. In programming, Hello World is considered to be a minimum working example, which means that it is the simplest bit of code to demonstrate that you can create and edit a script, you can successfully execute that script, and you can successfully use it to print to the screen. Printing content is highly valuable in code development and debugging. The command window is a great place to start by testing one-line code snippets. To print the message Hello World to screen, type the following command, disp hello world, and hit enter. It prints out the exact same text, Hello World. In MATLAB, there are actually multiple commands that can be used to print text to the screen. The disp command, which we just used, and the fprintf command, which can also be used to write data to a text file. fprintf is the recommended command for formatting outputs because, as this lecture will demonstrate, it is capable of printing more complex messages than disp. Now, with such simple string inputs, just saying hello world, both commands output the same thing. This will change in future slides. To write a hello world script, first recall how to create one from the previous lecture. Create and save one with the name Hello World in order to write the code in this example. The complexity of the code will be increased just slightly from the previous example, which was shown in the command window. By declaring a variable with the message text and passing that as an input to both commands, we avoid having to type the same text twice. Here, the variable core message stores the text, and it is referenced by both commands as an input. The output of these two commands is shown here. Again, with such a simple string, both commands produce identical results. Now, fprintf also enables formatting inserted data from variables into a core message. This is very valuable for creating log messages that print throughout a script and track the values of key variables. For example, it would be helpful to track things like the load capability and the design configuration in a script that optimizes a bridge. The following snippet shows the ending of such a log. In line 1, quote, at angle equals 75, bridge held load of 4870 newtons. In line 2, quote, maximum performance index of 1.623 at an angle 42 degrees. And in line 3, quote, bridge expected to support 3380 newtons at this optimal angle. In these messages, it first logs the load capability of the final bridge configuration that was tested, and then it logs the maximum performance index, its associated angle, and then its expected load from the entire optimization run. There are many different formatting codes that specify things like data types, the degree of precision, the number of total characters, and more. The following examples are just a few conversion characters that are likely to be the most relevant for this course. The first print command uses a %d to specify encoding an integer. The second print command uses a %f to specify encoding a floating point value, and the third command uses %s to specify encoding a string input. If we return to the logging example from earlier, the first line contains two numeric values, angle 75 and a load of 4870. Both of these were extracted from integer variables within the script, so the print statement might look like this. fprintf quote, at angle equals %d, bridge held load of %d newtons, end quote. And the next two arguments are theta and load, where both of those are variables from the script. The second line of the output contains two numeric values as well, the maximum performance index 1.623 and an angle 42 degrees. Both of these are again extracted from numeric variables within the script. the print statement would look like this. fprintf quotes maximum performance index of 0.3f at an angle %d degrees, with maximum pi and optimal angle passed in as variables from the script. Note now that the use of ellipses here puts a line break in the code, which can make the code more readable by preventing long lines. The third line only contains one numeric value, 3380 newtons, that it is expected to support. This value is also extracted from a variable in the script. The print statement would look like this. fprintf, quote, bridge expected to support %.2f newtons at this optimal angle, with again a line break, and the argument load at max pi angle is a variable taken from the script. To have an explicit review of all the formatting codes that can be used in injecting a variable into a message, MathWorks provides the following information. Formatting a variable must include the leading % character and the trailing conversion character. The earlier examples utilized %d, %f, and %s, but there are more. The rest of the formatting codes are filled between the % sign and the conversion character in the following manner: a numeric identifier, any modifier flags, a field width, the precision, and a subtype. The numeric identifier instructs the output to print a specific argument of the fprintf command. Take the following example statements. The first one here uses $1 and prints out 15. The second one uses $2 and prints out 9.876. So the identifier specifies whether to print argument 1 or 2. There are 5 allowed flags. The minus sign, left, justifies the content. The plus sign either prints a leading sign character or it right justifies the content. A space inserts a space before printing the value. A 0 will pad the printed output with zeros instead of blank spaces, and the pound modifies some numeric conversions. Including a minus sign, as in %-s, left justifies the text argument, and including a plus sign, as in %+s, right justifies that text argument. For example, consider this statement. The first injection here has a minus sign and the second has a plus sign, and as you can see, the word hello in the first printout is justified to the left and the second printout is justified to the right. Now for numeric values, including a plus sign, as in %+5.2f, will print a leading sign. For example, consider the following print statement. Both injections here use the same code, but one of the two arguments is positive and the other is negative. Both of them print with a leading sign, even though a positive value would normally not have one. So the plus operator changes its behavior according to the input. For text, it right justifies the argument, and for numeric values, it always prints a leading sign. A 0 flag, as in %0.5.2f, pads the printout with zeros. For example, consider the following print statement. We use a 0 here to print out around the value 12.3, and that prints out an additional 2 zeros before the actual numeric value. This fills in the space of the field width, which is discussed more in a couple of slides. The pound flag, the last one, as in %pound5.2f, modifies some numeric outputs. This flag is more complicated and won't be included in this course content, but you are welcome to read more about it on MathWorks' website. Now the field width specifies how many total characters the formatted output will occupy. There is a minimum width set by the value being printed, and you cannot override this, but you can increase the width above the minimum. Take this example. Here, the first printout is the default width for exponential notation. The second printout attempts to decrease that width, but it fails. The third printout increases it, and it does succeed. The fourth printout here is the default width for fixed point notation, and the fifth increases that fixed point width, and it does succeed. Now, as engineers, our work often has relevance in the real world, where precision is dictated by the physical limitations of the machinery that we use. Pair that with the fact that computers represent numeric values using the floating point format, which you can research through this hyperlink in the PDF, and there is plenty of inherent imprecision. Even with just the floating point numbers, single precision values are precise to 7 digits, and double precision are precise to 15 digits. These facts about precision are important when we interpret our work. The precision in string formatting specifies the number of decimals to print. Take this example. The first input here uses 0.1 to round to the tenths place, and the second input uses 0.5 to print out 5 total decimals. Now the subtype specifies that for the octal, hexadecimal, and decimal conversions, that the input should be treated as a floating point value instead of as an integer. These conversion characters will not be included in the instruction material for this course, but again, you are welcome to read more about the subtype on MathWorks' website through this hyperlink. Now in summary, this lecture covered what a hello world is, which is the simplest demonstration of executing code in a new programming language. The command window can be used to execute commands directly and to demonstrate printing basic hello world text. Those text commands from the command window are then written in a script, which also uses a variable as its argument to avoid writing the same text twice. Then, for the purpose of writing log messages, MATLAB enables you to use various formatting codes to inject data from variables to keep track of important quantities. And finally, we covered the details of how to format variables and the various codes associated with that process, including the identifier, flags, the field width, the precision, and the subtype.